what I thought I would do today is, given the wide range of audience here, basically give you sort of an introduction and maybe a selective survey in work on robust mechanism design that Stephen Morris and I have been pursuing for a number of years. And so I will probably talk for a while and then just stop. So we'll basically begin with sort of with the canonical, the canonical setup of mechanism design and implementation are really literatures who have been very successful in the past few decades, and both on a theoretical level, but also in terms of the application that the theory has actually found. One common criticism in the transition from the theoretical development to the application is that often the proposed solution of the theoretical models seem rather complex, difficult, and so in the application you will often find simplification or restrictions imposed on the nature of the optimal mechanism in order to respond to some perceived weaknesses or fragility of the theoretical mechanism. And so notions which are basically as old as mechanism design. In fact, Hurwitz already proposed a non-parametric approach to mechanism designs. Our work like simplicity, our work like non-parameter-free or detail-free, distributional-free, and notions like dominant strategy and exposed equilibrium, which are meant to reflect some kind of restriction on the problem. Okay. We want to sort of take perhaps a step back in this research, and we want to say, well, if it's the case that the theoretical problem seems too complex or too subtle relative to the situation, then maybe it's because the way we originally formulated the problem didn't really incorporate the constraints that we should have thought of right from the beginning. And so that suggests that basically one could sort of think of improve or augment the traditional canonical model of mechanism design, and then maybe endogenously generate some of the simple feature, the detail-free feature, the robustness features, which we commonly see in the applications. Okay, and in this talk and in this approach, we essentially want to say that we want to weaken the informational requirements, okay, and in particular we want to weaken the assumption that the planner shares a lot of common knowledge with the agents. Okay, and that idea that one wants to weaken the information assumption, in particular wants to weaken the assumption of shared common knowledge, really has been encapsulated in, we'll just talked in the foyer on it, what has been called, I think Eric dubbed the other Wilson doctrine, as it were, by Bob Wilson, which is sort of encapsulated really in a very nice quote, which I took from his presidential address, I guess 2 decades ago. And what he posited there, so let me read it for you, is that game theory has a great advantage in explicitly analyzing the consequences of trading rules that presumably are really common knowledge. Okay? But then he goes on to remark that it is deficient to the extent that it assumes other features to be common knowledge, such as one agent's probability assessment about another's preferences or about the information that other agents have. Okay? And on the basis of that, he then really proposes a program of research which says that I foresee the progress of game theory as depending on successive reductions in the base of common knowledge required to conduct useful analysis of practical problems. And it's almost an operational definition by saying that only by repeatedly weakening of common knowledge assumptions will the theory approximate reality. Okay, so that's basically in a snapshot the point of view that we took in this research, and we want to say let's weaken the informational requirements. And our canonical model of incomplete information as proposed by Hazani and then further formalized by Merton Samir, is really ideally suited to this operation, because there's a sense in which it's quite naturally to relax the common knowledge shared among the information by simply looking at larger type spaces, that is, by endowing the individual agents with more private information, and in consequence diminishing the amount of common knowledge that is in the system. Okay? And so there's a sense in which by looking at larger and larger type spaces where we distribute more and more of the common information into private information, we're looking at situations where we actually make fewer and fewer assumptions about the shared information of the agents. Okay? And so while Hazani, Merton, Samir really showed that there's no loss of generality to think that there's common knowledge about the type spaces, this really requires to look at large type spaces, whereas in our economic canonical models, we typically have very small type spaces. Okay? And the smallness in the type space, yet under the assumption of common knowledge, is in general problematic, but as some recent papers, in particular the paper by Niemann and others have shown, it's particularly problematic in the context of auction theory and mechanism design. Okay? So, as this is sort of a little bit of a survey, maybe let me start at our beginning, which was around maybe 2000 when we started to work on this. And the idea was to say, let's try to bring the language of richer types, of type spaces, of higher order beliefs, into the literature on mechanism design. Basically, sort of first make explicit what have been the implicit assumption on common knowledge, and then try to gradually weaken the common knowledge assumption and see what that does do to the nature of the mechanism and whether the mechanism then still can perform the required tasks. Okay? And so what we thought we could do was sort of get a few abstract results and then move on rather rapidly to sort of link this then to the actual applications. And I'm sorry to report that we're basically we just completed at point 1. Okay, so that's basically sort of a little bit of a survey, and I think that I'll basically give you sort of an idea what's the motivation behind this line of research, what are some of the key results, and leave it as that. Okay. A common feature of this entire set of papers is that they share a common environment. So I will give you sort of the general environment first, but then rapidly specialize it to sort of a simple example, and then show you by means of the simple example in a single unit auction what are sort of the main implications of our results for this example, and then leave the generalities for another time. Okay, but just so that you have an idea what is sort of the general environment for which we propose these results. It's a canonical model of a mechanism design where there's a finite agents. Each agent is endowed with some private information, which we refer to as payoff type, because that is really the information which determines its evaluation in terms of the utility function. There's some social outcome A, and the utility function the evaluation of a choice by society will depend on that allocation and on the payoff type profile of the other agents. So in particular, that allows the agents to evaluate his utility not only on the basis of his own information, but also on the basis of information that other agents may have. Okay? So we were basically in an environment with interdependent values, and the case of private values is naturally embedded in that. And what the mechanism designer would like to do will be basically define a mapping from the payoff relevant types into some choice in the allocation space. Okay. I call this the payoff environment, which we want to keep fixed, because that's really all the information that we need in order to evaluate a particular outcome, both from the individual point of view and from the social point of view. Okay? But in general, agents may have information, may have private information way beyond what is encoded in the payoff types, right? They may have information not only about their own preferences, they may have information that is beliefs about the payoff types of the other agents. They may have beliefs about the information of the other agents. They may even have higher order beliefs. All this is sort of captured in the canonical Bayesian model of type spaces. Okay? So a generic type space is then denoted by Ti, and that type will have in itself encoded information both about the payoff relevant type theta I, but it will also have encoded in it information about the likelihood of other agents to be of certain types. Right? And with the results of Mertens and Zamir, we can sort of think about as there being equivalence between these type spaces and sort of hierarchical information of types where beliefs over beliefs over beliefs. Okay? And so in the canonical Bayesian setting, a type space then is simply a collection of these types and mappings which specify what kind of information is conveyed in the type or by the type over its payoff environment and also over the beliefs of the other agents. Okay. And we basically are interested then in specifying larger and larger type spaces which give more and more information, make more and more information private, and make less and less information common. Okay. So here's exactly the example that I want to basically go through with you and sort of illustrate some of the results, which is basically the just a single unit allocation. So think about this as a single unit auction, if you wish, where each agent has a payoff type. Let's just assume it's somewhere between 0 and 1. And the valuation of the agent will depend on his own payoff type and possibly on the payoff type of the other agents. Okay. All agents have quasi-linear utility, so that their net utility is simply their gross utility from getting the object if they assigned it minus the transfer utility. Okay. This general class of interdependent value models, Eric defined it first in 92 and then elaborated on it with Saskia. Okay. But what I emphasize is that in this specification of the model, we only think about the payoff types. We do not specify at all what the beliefs of the agents are about each other, and in particular what the higher order beliefs are. Okay. So let me be specific or give you sort of narrow it down further. In a private value model, of course, we have the fact that my valuation depends only on my own private payoff type. If we are interested in efficient allocation, then we can run a second price sealed bid auction, a Vickrey auction, in which each agent makes a bid, and I don't have to remind you what the rules of the second price auction is. Let it suffice that there is basically an efficient allocation of the object, which simply is to give it to the person with the highest valuation. And associated with it, we can find transfers, which then also implement truth telling as a dominant strategy. Okay. Okay. We want to go beyond private values. So the leading example for this talk of interdependent values is simply one where my valuation is a linear combination of my own payoff type plus some weighted average over the information of the other ones. So you can think basically as gamma as a parameter which sort of measures the strengths in the interdependence of the preferences. A positive gamma expresses positive interdependence, a negative gamma expresses negative interdependence. That will be sort of information later on. Okay. Can we get an efficient outcome in this interdependent value model? And the answer to this was first given in the earlier mentioned paper, where one shows that basically a generalized sort of Vickrey-Groves-Clark mechanism indeed implements the efficient allocation. Okay? What happens here is that each player sort of is making a bid or is reporting a type, and what he assessed is not the second highest valuation, but what he assessed is simply the second highest bid plus the weighted sum of the bids of the others, because that's sort of to reflect the value of the interdependence. Okay? And the important thing to notice here is that we'll get efficient implementation in the direct mechanism. Okay? but the equilibrium is not going to be dominant strategy anymore. It's just going to be an exposed equilibrium that is given that everybody else is reporting truthfully. I will also have an incentive to report truthfully, and I will be happy to report truthfully, even conditional on the other agents reporting. So there's no averaging, no taking expectations here. This is through profile by profile. Okay. Okay. So let me just quickly give you sort of the formal definition before we then can start stating the first results.
Just for my information,
absolutely,
does that result depend on having the same gamma for all the other agents, or would it work if you had different gammas?
No, this is it doesn't work for all gammas. So the importance, and that's the result in Eric's paper, is that one needs to have a bound on the interdependence in order to get incentive compatibility, and that bound is that at the margin, an increase in my own signal has a stronger impact on my own valuation than on the valuation of the other agents.
What I'm asking is if that's where
but you're absolutely right. But these could be the gamma ij's could vary across types, across matches. That would all be fine. I'm just formulating it here for the simplest case because I want to do some calculus and it's going to be easier with a simple gamma. But it's actually nice to know that it works for general one, and we'll see some results for general gammas later on. So all this is here just for simplicity. Okay. So just to emphasize what an exposed equilibrium is, and also to emphasize that in private values, this notion actually coincides with dominant strategies, but in interdependent values, these two notions are quite different, and in fact, it's unlikely that dominant strategy equilibria do exist in models with interdependent values. Okay. Formally then, just to sort of to point out the difference between sort of a Bayesian notion, which takes into account all the information, and an equilibrium notion or an incentive compatibility notion of exposed. The exposed equilibrium in the direct mechanism, as it were, would simply say that is for all possible type profile that the other agents could have, if they report truthfully, that is, if their true type and their reported type coincide, then I have an incentive to also report my type truthfully. And that's true for all type profiles. An interim or a Bayesian equilibrium notion, which would simply say, well, given the expectation or given the information I have with my type, and given therefore the expectation that that engenders about the types of the others, I would like to tell the truth. So we're taking here then expectations with respect to our information and requiring the equilibrium only to hold in expected values rather than profile by profile. Okay, and I should have omitted, so I should have, well, it's actually correct, it says, but a dominant strategy simply would say, in this interdependent values context, just to emphasize the point, that I'm happy to tell the truth irrespective of what the other agent's telling me, in particular irrespective of whether their reports coincide with their true types. Okay.
I thought you'd set up so that the social choice function was defined on preference types.
Very good. So if we restrict ourselves to just Bayesian implementation, or I call it interim because we don't necessarily need even a common prior in this environment here, then of course I would have the freedom to possibly use information other than the payoff types in order to get incentive compatibility. So then there's no reason for me to restrict myself to be just measurable with respect to the payoff types. I could allow to use and extract other useful information.
So you're only imposing that when you're talking about exposed.
That's exactly right. Thank you. Okay. So here's the first question that we want to ask. Okay. We want to find conditions under which we can identify a mechanism with a property that this mechanism implements the social choice function. Let's think simply about an efficient allocation for any beliefs and higher order beliefs that the agents may have. Okay. So not only is it a mechanism which works for a particular belief structure, but it in fact works for all possible belief structure. That's the sense in which we would then like to say that this mechanism solves the incentive problem robustly because it solves it for a wide class of beliefs. Okay. So in our single good example, the efficient correspondence is where we choose the efficient assignment and then find a particular transfer scheme which implements that would be such a desired solution. Okay. And from my argument, it should be clear that the notion of exposed equilibrium and exposed incentive compatibility is indeed a sufficient condition for this robustness requirement. Okay. The question is it also necessary? Okay. And so here, if you want to think about what happens if we sort of increase the type spaces, is that we actually give the agents more and more private information. In turn, we basically create more and more incentive constraints. So we impose more and more restrictions on what the designer can do and how he can respond to the information. As we add more and more incentives constraints, the constraints become more severe. And the question is, in the limit, can we still satisfy these constraints? And what's the nature of the social choice function that it has to satisfy in order to satisfy this multitude of constraints? Okay. And so we can sort from small type spaces to largest type spaces in the language of Merton Samir, the universal type space, and that gives us sort of a whole range. And so one of the earlier results in this literature was precisely an equivalent statement, which is to say that a social choice function is exposed incentive compatible if and only if it's interim incentive compatible for all possible time spaces. Okay? And that result can be generated, can be generalized, as stated here, for social choice function to social choice correspondences with some structure, in particular with sort of a product structure. And it's important to note that this is actually it's not going to be satisfied for all social choice functions. So, for example, the efficient allocation, which about the balance, fails this requirement of the product structure. In fact, we can show that the equivalence result there doesn't hold. So it's imposing some bite, but it allows us to solve for a large class of problem in a robust way. Okay? In other words, we can think about exposed equilibrium basically as an equilibrium notion which encodes or incorporates robustness to higher order beliefs. Okay? If you think sort of about the issues of simplicity, that's also nice because it's much easier to compute the exposed incentive compatible transfers than it is to compute transfers which satisfy Bayesian incentive compatibility. That is a verification. It's much easier for exposed because we don't have to take expectations. That operation is omitted. Okay. And this is really sort of a natural extension and generalization of results established in the late 70s on the robustness of dominant strategy, or the interpretation of dominant strategy as being a robust implementation in private value environments. And what we do here is sort of extend that environment to interdependent values and see whether we can find sort of a similar encoding, and it turns out that that's the exposed equilibrium. Okay. So this first result, to rephrase that, says that basically in the direct mechanism, truth-telling is going to be an equilibrium for all possible type spaces if it's the case that the social choice function satisfies the exposed incentive constraints for all the agents and at all the type profiles. Okay? But that simply says that we can identify one equilibrium in this in this direct mechanism, which has the property, and it suggests another question, namely to ask whether in fact it is the only equilibrium, or whether all the equilibria lead to the efficient outcome which we want to achieve, or might there be other equilibrium lurking in this mechanism which would achieve outcomes far from what we have desired. Mm-hmm.
In the statement of the theorem, I'm thinking about the right to left direction. So
yes,
I'm wondering if you need to use every type space to get that direction, or if you really need to use
no. So
beliefs.
So it's a very nice point that in fact to get this equivalence we don't need to have the universal type space. It is we only need common prior type spaces, and we don't even need all common prior type spaces. In some sense, the complete information type spaces are the critical type spaces which we need in order to establish this result. So that's very good. So we don't need the full strength of the universal type space in order to get this equivalence. So very, by the way, that sort of qualification is true for the social choice function, but for social choice correspondences, actually turns out that you sometimes would like to use larger type spaces in order to get the equivalence. That is, for social choice correspondences, it is often the case that this equivalence statement is not going to be true just with common prior type spaces, but you need larger type spaces in order to make it work.
Just a clarification, is there a revelation principle on each side of this equivalence that would justifies looking at truth telling?
Yes.
Okay.
Yes. Okay. So I mentioned that we could now naturally pursue this and say, well, are there other equilibria, or are there conditions under which, in fact, all equilibria in this mechanism will lead us an ex post equilibrium? Okay. That is, what we could ask for is whether we have full implementation under the solution concept of ex post equilibrium, and we then follow sort of the literature by saying we refer to that as ex post implementation. That is, all equilibria lead to the desired outcome. And here one can establish a result of ex post monotonicity, which is familiar both from the complete information literature and to the incomplete information literature. And of course, massive monotonicity, so the notion for complete information. Interestingly, even though the notion of ex post has a flavor of complete information, as sort of you have suggested, the condition of ex post monotonicity is neither implied nor does it imply masking monotonicity. Okay, in particular, in our example, surprisingly, the direct mechanism, namely the generalized VCG mechanism, in fact satisfy the ex post monotonicity condition as long as we have interdependent values and as long as we have 3 or more pairs. So that's a strong implementation condition in the even in the direct mechanism, which is a little bit surprising. Okay. But now we phrase the problem actually a little bit too narrow in some sense, if we are concerned with robustness, because all we have addressed now is the fact that there do not exist non-desirable ex post equilibria, that is, there do not exist non-desirable equilibria which has a strong robustness property. But there might exist other Bayesian interim equilibria which are still part of that mechanism and which therefore would sort of violate the spirit of getting implementation in a robust sense. Okay. So we could, and we do, ask this question in a little bit stronger form by saying, can we find a mechanism, or what kind of properties would it have, so that for any beliefs and higher order beliefs, the desired outcome is an equilibrium and no other outcomes do form an equilibrium, and now by equilibrium we really mean just interim equilibrium. And if we can guarantee that property, then we want to think about this as satisfying or achieving robust implementation. This implementation with respect to all beliefs in higher order beliefs.
Is interim equilibrium just Bayesian equilibrium?
Sorry, I should have said that since the type spaces don't necessarily have a common prior, we don't want to refer to it as Bayesian. We simply want to say, given the interim information that the agents have, I want the incentive conditions satisfied. So it's a sort of a natural generalization to emphasize the point that we don't necessarily require common priors here. Okay. And it's sort of known that in the private values case, a robust implementation fails because telling the truth is just a weak best response. There are many equilibria which don't lead to the efficient outcome. Okay, and so robust implementation is not possible even if we look at a larger and augmented mechanism. And so what we suggest here is to say, well, can we get robust implementation for nearby, for almost efficient applications? Okay.
By strengthening the equilibrium concept a bit, you can rule out these other equilibriums. So in a Vickrey auction, if you impose that strategies not be weakly dominated.
That's exactly.
I can't remember. Have you looked at that?
So the operation that I'm just suggesting shortly is basically the dual operation to what you're suggesting, rather than eliminating weakly dominated strategy. We just change the mechanism a little bit that truth telling becomes a strictly dominant strategy, and we do that because for the analysis, and especially for sort of its epistemic foundations, it's much nicer to think about a strict dominance rather than weak dominance. Okay. So here's, in our little example, a simple modification of the mechanism which would do the job. Basically, we're staying with our efficient allocation with high probability 1 minus epsilon, and with a very small probability, we're going to give the object with a probability which is increasing in its own bit to agent I. Okay. Since now the allocation and the payment depends with a small probability on my bits, we basically restore the fact that truth-telling or truth-forbidding is a strictly dominant strategy. Okay? And so therefore, in the private value environments, we can guarantee robust implementation, but of course at the cost of relaxing efficiency to epsilon efficiency. But that's what I meant by sort of. Things are not quite as easy when we now go to the interdependent value environment. So we can use sort of the same idea of strengthening, in some sense, the responsiveness of the allocation to the report or to the bit, so that truth-telling becomes now a strict exposed equilibrium and removes the weakness in our original relations. Okay? But that alone turns out is not sufficient to guarantee to guarantee robust implementation. Okay. And sort of the remaining time, I want to sort of convince you and give you sort of a series of arguments to show you that when we think about robust implementation in interdependent value environments, there's a new condition occurring which relates to the strengths in the interdependence of preference and the independence of information in the environment. And the result that I will arrive at the end is to say that in the interdependent value environment, we can achieve robust implementation. We can achieve robust implementation, but at the cost of restricting our environment to allow for only weak interdependence. That is, the parameter of interdependence, which early on had to be just bounded by 1 in order to get incentive compatibility, now needs to be bounded by 1 over the number of agents in the symmetric environment. There's a more general condition for non-symmetric preferences in order to get a robust implementation. And an interesting side aspect is that if this condition is satisfied, then we can get robust implementation in the direct mechanism. On the other hand, if it fails, then we can get no robust implementation, neither in the direct nor any augmented mechanism. Okay. And in fact, your comment earlier on using weak versus strict is paralleled in an earlier paper by Chung and Ely, where they look at the single unit auction and use weak elimination of weakly dominated strategy and basically obtain the same results for sufficiency, but then because of using the weak elimination, they can't get necessary conditions which we can obtain here. So that's one additional. Okay. Yeah. So that's sort of the last result I want to report and give you a little bit of a flavor of what is going on. What we're going to do here is now, in terms of the argument, quite a bit different from the truthful implementation, because we're going to use an epistemic result, which has long been established in the complete information literature, and which now makes its way into the incomplete information literature. And it goes as follows. We want to establish a relationship between an equilibrium on n type space, on a arbitrary type space, and the class of actions which we want to call rationalizable actions. So in the complete information literature, there's an epistemic result which says basically that there exists an equilibrium in some type space, that is for some information, if and only if these strategies are part of the rationalizable actions. And that result is also true in a world of incomplete information. And what this allows us is, rather than looking at all possible equilibria on larger and larger type spaces, or even universal type spaces, we can rephrase this question in terms of an iterative procedure, namely rationalizability for incomplete information, in which we don't have to refer at all to the large type spaces, but an iterative procedure which is simply defined on the smaller type spaces, just on the pair of type spaces. And it's this iterative procedure and sort of a contraction property which then leads us to, in the specific example, to the result that gamma has to be smaller than 1 over the number of agents minus 1. Okay. So what's the key epistemic result? That is to say, if you think about general mechanism, that a mechanism or a message mi can be sent for an agent with a pair of type theta I in some interim equilibrium on some type space, if and only if we can show and establish that this message is rationalizable, that is, can be a best response to some conjecture by agent I about the messages of the other agents. Okay? And this notion of rationalizability is basically the solution concept is implemented by a recursive procedure, where we'll first start out by saying, well, we can't impose any restriction on what an agent could do, and then we slowly eliminating possibility, this is possible messages that an agent could do, given that those messages can't be a best response for any possible beliefs that he entertains about the other agents. And by recursively eliminating more and more of these messages, we might eventually come down to a fairly good description of what are rationalizable in the sense of best responses to some conjectures. Okay. So in the generalized BCG mechanism, the direct mechanism, a message is simply a report that an agent makes, truthful or not. And a conjecture is then simply a probability distribution over the reports that the other agents may make, or not as a function, and the types they are going to be. Okay? And we could simply say, in this iterative process, in round k, let's call beta I of k those messages of agent I with type theta I, with a particular pair of types, that are rationalizable in the sense that there exists some conjecture that agent I has about the other's opponent's types, as well as reports. Okay? Given that these reports, with subject to the restriction that these reports are still conceivable, that is, at least have not been eliminated in the process before, and then iterate this procedure. Okay. One of the reasons that I chose to work with this linear model here for this talk is that in the linear model, this procedure is really quite accessible, and we can sort of do the calculations as we go. With linear interdependence, as it were, the exposed incentive compatible transfer is quadratic, and therefore the best response of an agent to point beliefs is simply a linear best response. Okay, so that if agent is of type theta I, and he believes that the other agents have a type profile theta j, but report something possibly different, namely theta j prime, then his best response is simply to report his true type plus a weighted sum where this sum reflects the differences between the reported type and the true type. So in some sense, he's trying to offset the misreport that he believes the other agents are going to do. And of course, the immediate verification is that truth-telling, that is the agreement of report and type, is indeed an equilibrium because it's satisfied the best response problem. Okay. But due to the linear structure, we can now basically characterize a set of best responses in terms of a lower bound or an upper bound, and iterate this process to basically see whether these bounds converge and what are the conditions so that these bounds converge. Okay. So let me just remind you, this is the linear best response. Okay. In any particular round, what is sort of the largest possible report that I could make while I'm type theta I? Well, I can't go more than one. That was our a priori bound on the types. Okay. What's the largest type I could choose? Well, let's just suppose that gamma is positive for the moment. Then that's that report which is sustained by beliefs of agent I about the remaining agent, which make this difference as large as possible. Okay. But of course, what are those types? Well, these are the types which basically have assumed the lowest possible reports being submitted by the other agents. So we basically determine the upper bound of agent I in terms of the lower bound of all the other agents in the previous round. Okay. In this linear environment, this is really just an iteration on this operator gamma times I minus 1, because initially the maximum difference between type and report is 1. There are I minus 1 agents, and the weight that we're giving them is simply gamma. Okay. So then we basically iterate in each round and raise this difference to the power of k, and therefore the question then resolves simply, is it going to be the case that eventually I will just be left over with reporting truthfully? Well, that's the case if and only if this expression converges to 0 as k goes to infinity, which is basically to say the weight gamma has to be strictly smaller than 1 over I minus 1. Okay. And so that gives you sort of the sufficiency, and in this example it's easy to convince ourselves that it's also necessary, because let's just take a particular belief that agent I has over the types of the other agents, okay, which depends on his own type. So it's exactly calibrated in some sense, such that actually his expected value of the object is independent of his own type. That is, his belief of the other agents varies sufficiently so that in expectation his expected value of the object does not depend on his own type. And since that's the case, now it's going to be impossible to separate two types through incentive constraints and through rewards, because all of these types have the same belief about what the value of the object is. So that basically shows you that this is both a necessary and sufficient result, and it's basically determined by the strength of the interdependence. Okay. Let me just perhaps sort of to give you the idea how this condition looks on the general environment, to sort of convince you, at least hint that the specifics of the model don't matter here. So let's simply think about the generalization of this model, where we basically have a compact type space for each of the agents, and where the preference that agents has are going to be determined to an aggregate of the payoff types of all the other agents. Okay. And in order to get incentive compatibility, we want to assume that the preferences are single crossing in this aggregate. Okay. So clearly, the linear model I just proposed to you has this aggregation property, but a very specific one. Okay. Then the general result is that robust implementation is possible in a direct mechanism if and only if we have strict exposed incentive compatibility and this contraction property is satisfied. Okay. That I mentioned early on. And what is this contraction property? It's basically a statement which is to say that my own preferences or my own information, that is the difference between theta I and the valuation of the object with another reported type, those changes induced through my own type are large enough to offset any other changes that could be introduced into my preferences through variation in the type of the other agents. That is, I can always find the same sign in terms of the variation of preferences induced simply through changing my own type and changing all of the other agents' type. Okay? And then this condition in the linear model is just equivalent to this bound. And if you think now sort of a generalized linear model, which you had presumably in mind, right? Yeah. Where now my value or my aggregate is simply a weighted aggregate which can depend both on my own type as well as the type of the other agents, then we can think about gamma, which is simply the entries of the interaction terms as basically sort of the interaction matrix, the interdependence matrix. Okay? Removing the off diagonal, which basically says, well, how strong are these interdependences, and taking the absolute values. Okay? Then here sort of one can use a classic linear algebra result, or reduce it eventually to a classic linear algebra result, which says that the contraction property is satisfied if and only if the eigenvalue of this interaction matrix, so the modulo of the interaction matrix, has an eigenvalue. The largest has an eigenvalue smaller than that. And that basically guarantees that this contraction property proceeds and eliminates more and more messages until it singles down on truth telling just be the only result. Okay. So I don't think I have time for that. Let me perhaps just sort of give you an outlook, given that we sort of proceeded slowly the first time around. Especially if you're coming sort of from a used to other notions of robustness, what will strike you here is that when we speak about type spaces, we sort of require large robustness in the sense that we are allowed for all possible beliefs and higher order beliefs. And so it's natural to think about sort of more local or intermediate notions of robustness, or restrictions on the type space that maybe a common prior or a common prior over the pair of types is satisfied to get a little bit more heavy. We also focus very much on efficient allocation problem, and it's still an open question whether and how one would go about proving sort of robust predictions for revenue maximization problems, which inherently will have to be phrased with respect to the beliefs that the agents have. There are other sort of minor issues, which is to say, well, can we sort of restate single crossing conditions in rich type space in an interesting way, which sort of reflect the interdependence? And I think our interest is more sort of using the insights we got from mechanism design, which we really were quite helpful in terms of designing exactly the mechanism so that we get strong robustness results, strong positive results. More generally in games with private information, where typically we won't get such strong predictions, robust predictions in terms of just points, but we could ask whether we can get sort of set predictions, partial predictions, in terms of what is the distribution of outcomes in a class of games if we allow a set of possible beliefs.
Thank you. We actually do have time for a couple of questions. So I assume you'll just handle them yourself.
Yes, there are.
So what are some sufficient conditions for that contraction property? Are there any some strategic complements or so?
Yes. So actually, no. I wanted to go back maybe just to see whether I can find it on the
list. The sum of the weights is less than one sufficient.
That's right. So notice that the condition we had was a necessary and sufficient condition. But it was formulated in terms of not the value, but the absolute value of of the interaction. So for the contraction property, actually, complementarity substitution doesn't play an important role at all. So whether they're all positive or all negative, that doesn't play the role. What is needed is the case that the radius of the interaction is bounded. And for that, all that matters is the absolute value rather than the sign or the direction of the result. But that's, that was one of the last results which I could have taught. That is only true if we look at the notion of rationalizability, and in particular don't impose any common prior assumptions. When we impose common prior assumptions, so that's a natural question to say, let's at least assume, possibly over large type space, that the agents share common prior, then the sign of the interaction matrix actually makes a big difference. It is, then the results are going to look quite different for environments where we have strategic complements as opposed to environments where we have strategic substitutes. So that's part of our thinking, is that it might be interesting to look at these intermediate cases because we want to know how important is the common prior for predictions, and can we really get, when is it that we can get mileage or impose restrictions by assuming that the agent at least have a common priors in terms of sharing information. But for the notion of rationalizability, the sign didn't matter at all.
Was that your question? I thought the question was, what's the sufficient condition that the contraction property for that matrix holds, right?
Yeah.
And the sufficient condition was that the largest eigenvalue...
Right, but she said, what was the
weaker.
sufficient condition for example, if the row sums are all less than 1, that would be a sufficient condition, right?
Yeah, so then, right, so there are weaker sufficient condition in some sense, which are sort of, it's a classic literature in linear algebra on diagonal dominance and
Gersh-Gorin's theorem. Gersh-Gorin's theorem.
Yes, yes.
Well,
So I think there's a large class of
You get the same sort of thing out of raw Hurwitz too. I mean, it's just a stability condition of a difference equation.
yeah, but Ralph Hurwitz is pretty hard to apply
I
to
agree.
a large
It's
matrix.
not easy to
But
apply.
Gersh-Gorin's theorem
Yeah.
is pretty easy.
Yeah.
No, but I was trying to, I think I was curious about sort of if you can say something about the interactions, something that will guarantee.
Well, that's why I said, I think if the row sums are all, for example, or the column sums are all less than 1,
that would be sufficient.
Yeah.
that would be sufficient. And that's an easy condition. I was just wondering whether Perron-Frobenius theory helps.
Yeah, sorry, I was looking for this is actually what we used.
Yeah.
We used the proof uses Perron-Frobenius theorem.
Mm-hmm.
Well, then you're going to make sure that the dimension is high enough on that. To get the
Pardon me?
full- You need the dimension high enough, no larger than 2 by 2, because you're not going to have your 3 by 3 will work and a larger will work. But 3 by
No,
2
so it's just going to be, the dimension doesn't matter at all, it's just that the conditions are going to be different. Remember that the condition was that the gamma, the interaction, is smaller than I minus 1. So, exactly. So it's interesting that in the case then of just 2 agents, it reduces exactly to the conditional incentive compatibility, single crossing, right? Yeah. But as soon as we have more than 2 agents, what we find in some sense is that we need a qualitative restriction which is coming from the implementation characterization rather than from the truth-telling characterization.
Do you have any trouble with the Perron-Frobenius theory if a lot of those off-diagonal terms are zeros, or I don't remember if you assumed that they weren't zeros?
No, they can be zeros. I mean, they're just...
So then the matrix will not be necessarily irreducible.
See, it's the irreducibility condition that you need for the Perron-Frobenius theorem.
And that's why I
that's
asked
why
about
2
the
by 2
relation
gets a little
between the
difficult.
agents
But
to
when you get to
ensure
higher dimensions, if you have zeros in
irreducibility.
there, you're going to run into some difficulties. You might need another condition.
You know this better than the statement, which is true irrespective of the matrix, is the eigenvalue needs to be less than 1, and then
Yeah.
Sure.
for certain exactly. Then you can sort of think further what are sort of sufficient conditions for particular
But it
classes.
seems like the zeros ought to make things easier in a way.
Absolutely. So they make things
Because you
easier
can't use
because
the
You just can't use
Perron-Frobenius.
the Perron-Frobenius, that's all.
That's right. But maybe you can break it up into sub-matrices
Just sub-irreducible.
and apply it to each one of those.
absolutely. So for example, if you have local, so that's a very so we have an so if you have localized interaction, then of course you get sort of the conditions on the local interactions rather than on the global.
Because if it's reducible, then the maximum eigenvalue would be the maximum eigenvalue of the sub-matrices.
You just look at the different component parts.
Yeah.
so it's probably still